Okay, good day everyone. In this video, I will be answering activities under my Laboratory 7, which is focused on the stack. For Activity 1, a program is given, which purpose is to load values into each registers of R20 to R24, and then push each of these values onto the stack. So I am responsible for single-stepping the program and then examining the stack and the SP register after the execution of each instruction. So I have here 4 windows. The first and the second one is responsible for showing the results on the registers, and then this window is for watching these variables, and this one for examining, observing the stack. Okay, so I will be pressing on F11 to simulate the program. For the first instruction, we have here the constant ramen, which is based on a read. It refers to the last address in SRAM, and the ramen is usually 16-bit, so we have here the high and the low in order to break it down into 8-bit. Okay, so I will be pressing F11 to process LDIR20. Okay, so our stack pointer here is still 0, and then our R20 here became 08 hex, and here our R20 became 08 hex. This line, we see that the value on R20 is written to the high ramen here in the SPH, and our stack pointer is also equivalent to what is stored on R20. For this line, our R20 became 5F hex. We can see here from 08 hex it changed into 5F, but our stack pointer remained 08 hex. In this instruction, on the SPL, which stands for stack pointer low, we can see that 5F is loaded onto our stack pointer, and our R20 is changed into 5F, and it is loaded or stuck in our low ramen. Here our SPL equates to 5F hex. So these consecutive instructions will load these values to the mentioned registers. So for this one, we load 20 to R20. Next, we load 31 to R21. And then we load 32 to R22. On R23, 53. Then 64 on R24. For the following lines, instruction or command used is push. When we are pushing a register, it means that we are getting its value to be stuck on our SP register. For this instruction, push R20 from 5F, it became 5E. Then we push R21. So from 5E, our low ramen became 5D. And then pushing pushing R22, we have 5C. And then pushing R23, we have 5B. And then pushing R24, we have 5A. So we used here the instruction RJump instead of jump because to save byte, since our jump is for 2 byte only. We can also observe that our stack pointer, that our high ramen is not affected and it's still equivalent to 08 hex. So the total stack on our stack pointer is 085A hex. That's for activity 1. For activity 2, we were already given with a program that satisfy the given condition. So what will I do again is to simulate this program to single step and examine the registers, the stack, as well as the stack pointer. So I will start here pressing F11. I already click on the simulation button. Loading immediately R20 being 90 on the high. So there seemed to be no effect since our R20 remained on 0. Then copying it to SPH. There's still no reaction, so our stack pointer is still 0. Now, loading immediately or setting 90 at low SP. So we have R20 equivalent to 90. And then copying or putting the of R20 to our SPL, we're able to set the 90 to our stack pointer. So this means that our 90 is a low byte since it did not load in the high byte. Let's proceed to the next line. Load 1 to R16, and then we stored the value of R16 to 98. And then we load 2 to R16. Then we get the value of R16 to 99. We load 3 to R16 immediately. We copy the value of R16 to 9A through the instruction STS. We load 4 to R16. We copy the value on R16 to 9B. So we load 5 to R16. Value of R16 is stored to 9C. Then next, load 6 to 16. Then we copy it to STS 9D. As we observe, we used only a single register to load each numbers, but we store it into different hex values through use of STS. Now we can proceed to the next lines where we use the pop instruction. Oops, na-modify ko siya. So for pop R20, our stock pointer that's 9F, it's incremented by 1, which is it became 9E, and our R20 from 9D, it became hex FF. We pop R21, our stock pointer and our stock is now incremented again by 1, and from 9E, it became 9F, while our R21 also became FF hex. The same scenario happened when we pop R22, became FF hex, and our stock pointer is incremented by 1. And popping R23, we have FF registered or load on our R20 register, then our stock pointer incremented by 1. So it seemed that the pop instruction works reverse or oppositely to push instruction, since it was observed earlier that when we push registers, our stock pointer and stock decrement by 1, and our registers were not affected by executing each instruction. But this time, when we use the pop instruction, our registers were affected, and as well as our stock pointer increases by 1. To process the last line, we pop R24, R24 became FF in hex, and our stock pointer was again incremented by 1. That resulted into 0082 hex. So that's for activity 2.